In this video, we will learn about the elements that make up our universe and about atoms, which are the simplest unit of those elements. We'll look at what happens when atoms come together and at how we write and describe the combinations. To start off, let's have a quick look at the structure of atoms. Atoms are extremely small. A piece of coal that fits in the palm of your hand contains about 10 million billion atoms. That's 10 to the power of 25 atoms. Every atom is made of a nucleus and some electrons. The nucleus is the densely packed core of an atom containing protons and neutrons, and the electrons fill the surrounding space. One proton has the mass of about 1 unified atomic mass unit. That's 1/12 of the mass of a carbon-12 atom. We'll take a look at exactly what a carbon-12 atom is in a moment. Neutrons also have a mass of about 1 unified atomic mass unit, so for most purposes we treat protons and neutrons as if they have the same mass. Electrons are much lighter, with a mass of 0.00055 unified atomic mass units. You'll sometimes see this expressed as a fraction, 1 divided by about 1,840. This presentation tells us that it takes about 1,840 electrons to have the same mass as a single proton or neutron. The other key property of these particles is their charge. Particles can either have no charge or positive charge or negative charge. Particles with the same type of charge repel each other, so positive particles repel positive particles and negative particles repel negative particles. But two particles with opposite charge, one with positive charge and one with negative charge, will attract each other. Protons are positively charged, electrons are negatively charged, and neutrons have no overall charge. To make things simpler, we say that a proton has a single positive charge, and electrons have equal and opposite charge, so they have a 1- charge. Atoms can have different numbers of protons, neutrons, and electrons. For instance, a carbon-12 atom is an atom with 6 protons, 6 neutrons, and 6 electrons. Having more neutrons makes an atom heavier, and having more protons also makes an atom heavier. But crucially, adding more protons makes the nucleus of an atom more positively charged. The more positively charged the nucleus, the more electrons it can hold on to. By definition, atoms are neutral overall, so we need exactly the same number of electrons as we do have protons in order to classify it as an atom. All this boils down to a very simple definition of the atom. An atom is simply a nucleus with enough bound electrons to make it neutral overall. So the number of electrons for an atom is equal to the number of protons in its nucleus. So the number of protons in an atom's nucleus dictates the number of electrons it has. These two factors together determine the chemistry for that atom. The number of neutrons does matter, it does contribute extra mass to the atom, but apart from some very special cases, the number of neutrons in an atom doesn't affect how the atom reacts. This is why the very first way we classify atoms is by talking about elements. And then we use the number of neutrons to break elements down further into isotopes. But in this video, I'll just be looking at elements. An element is simply a type of atom based on the number of protons in the atom's nucleus. So let's imagine we've got an atom, we look inside its nucleus, and we count the number of protons. If there's 1 proton, we say the atom is of the element hydrogen. If there are 2 protons, then we say it's an atom of helium, and so on. There are, at the moment, 118 confirmed chemical elements, but only about 100 of these have practical applications at the moment. The heavier elements are very unstable and have to be created in supercolliders, and they break down into lighter elements in fractions of a second. The table shows us all the elements from the lightest, hydrogen, with 1 proton per atom, to the heaviest, organoson, with 118 protons per atom. You can use the periodic table to find out lots of information about an element, including its name, symbol, and atomic number. The atomic number is simply the number of protons in atoms of that element. Now that we've had an overview of the different types of atom, let's see what happens when we combine them together. We've already talked about how the type or element of an atom might affect how it reacts. If we were to separate out all the particles in the atmosphere, about 1% of them would be atoms of argon. What this means is that these atoms have 18 protons in their nuclei, and these atoms of argon also have 18 electrons each. For reasons that are beyond the scope of this video, argon atoms are unreactive, and so they go around in the atmosphere as an atomic gas. What this means is, when argon atoms interact with other atoms, they just bounce off. On the other hand, another substance to be found in Earth's atmosphere is oxygen. When we look at oxygen gas, we see the oxygen atoms going around in pairs. The two atoms share their electrons to some degree, and they bind together in a chemical bond. This is what we call a molecule, so oxygen in this form is a molecular gas. You might see the oxygen molecule as 2 of the letter O with 2 lines between them. The 2 lines indicate the number of electrons that are being shared. Or you may see them as 2 balls connected by a line, or 2 balls stuck together, or O with a little 2 next to it. The bond between these two oxygens is an example of a covalent bond. What this means is that the atoms are sharing their outer electrons. The nuclei are attracted to these shared electrons, generating the bond. When we have 2 or more atoms bonded together in this fashion, we call them a molecule. Molecules can have 2, 3, 4, 5, 100 or even 1,000,000 atoms. And they don't even need to be the same type of atom. Now, you may be aware that atoms can lose or gain electrons to form things that we call ions. Ions form ionic structures where positive and negative ions alternate in all directions. It's important to realize that these structures are not molecules. Now that we know what molecules are and are not, let's have a look at how molecules interact. Molecules can interact with each other and stick together to some degree. That's how you get solids like ice and liquids like drinking water. But the forces between molecules are much weaker than the bonds inside molecules. We call the forces between molecules intermolecular forces, and we call the forces inside molecules intramolecular forces. To help you remember these, you can think about an interview, a discussion between 2 people that maybe results in somebody getting a job. And you can think about an intravenous injection that goes into someone. Now, why are intermolecular forces important? It's because they control whether a substance is going to be a solid, a liquid, or a gas at a given temperature. Let's look at the intermolecular forces in ice, which is made of molecules of H2O, 1 oxygen atom bound to 2 hydrogen atoms. These intermolecular forces are strong enough to hold the molecules in place, making ice a solid. But if we heat up the ice above 0 degrees Celsius, we're going to melt it, and the individual particles of water can move over each other in a fluid way. If we heat the liquid water so that it boils, we're giving the molecules so much energy that they completely overcome the attractive intermolecular forces and they fly away as free particles, filling up the surrounding space. The stronger the intermolecular forces, the more energy we need to turn a molecular substance into a gas. Now let's have a look at how we might write down elements, atoms, and molecules. As you learn more about chemistry, you'll see elements, atoms, and molecules written in many different ways. For instance, you might see the word oxygen, which means the element oxygen. Or you might see oxygen atom, which means an atom with 8 protons in its nucleus, an atom of the element oxygen. Or you may see the words oxygen molecule, which refers to a molecule that contains only oxygen atoms. We would normally expect an oxygen molecule to contain 2 oxygen atoms. Now, it can get a little bit confusing when we're talking about the symbols, because the symbol for the element oxygen is the same as the symbol we'd use for a single atom. You'll have to use the context to figure out what's being described. But we already know that the symbol for the oxygen molecule is O2. You can think of this as two oxygens. You may see these formulas appearing with state symbols, which are symbols that indicate the state or phase of the substance. So you may see symbols like that, where we have the oxygen molecule in solid form, in liquid form, or in gas form. And you may also see the symbol AQ, which indicates a substance is dissolved in water. These symbols will crop up all over the place, for instance in chemical reaction equations. Here we have a carbon atom reacting with an oxygen molecule to form an entirely new substance called carbon dioxide. This new substance has different intermolecular forces and different intramolecular forces. We've gone over a lot about atoms, molecules and elements. It's about time we had some practice. Which of the following is not a molecule? A. CO2, B. O2, C. NO, D. N2, or E. Na? A molecule is two or more atoms covalently bonded together. An example of this would be a molecule of water, or H2O, where we have one oxygen atom covalently bound to two hydrogen atoms. We can use the periodic table to work out what the symbols in all our formulas mean. If we look up the letter C on the periodic table, we'll see that it stands for the element carbon. So when we look at our formulas, we can see whenever we see a capital C like that, it indicates we've got one carbon atom. O is the symbol for oxygen. So where we see O, we know we're talking about an oxygen atom. And when we see a little 2, that means we have two of that thing. So O2 means two oxygen atoms. This is the symbol for an oxygen molecule, two oxygen atoms covalently bonded together. So we know it's not the correct answer because we're looking for something that's not a molecule. The last symbols are N for nitrogen and Na for sodium. Element symbols are always a capital letter or a capital letter followed by a lowercase letter. So the N in Na isn't for nitrogen, it's just the beginning of Na for sodium. Now the main difference between sodium and nitrogen is that sodium is a metal and nitrogen is a non-metal. Now we can still get nitrogen atoms and sodium atoms, but non-metals tend to form covalent bonds and form molecules, while metals form metallic structures that continue in all directions and have very different bonding to the covalent bonding in molecules. So CO2, O2, NO, N2 all describe a molecule containing two or more atoms covalently bonded together. But Na describes a single atom, and it's a single atom of a metal that would be unlikely to form molecules in the first place. So of our 5 candidates, the only one that is not a molecule is Na. Now let's have a look at a slightly tougher question. What is the difference between a sulfur atom and a sulfur molecule? A. Sulfur atoms are reactive, while sulfur molecules are not. B. Sulfur atoms consist of multiple sulfur molecules bonded together. C. A sulfur molecule consists of multiple sulfur atoms bonded together. Or D. Sulfur atoms can be divided into smaller units, while sulfur molecules cannot. The first thing we need to identify is that sulfur is a chemical element. As with all elements, we can look up sulfur on the periodic table. We find sulfur in group 16, otherwise known as group 6, just below oxygen. If we zoom in a little closer, we can see a little bit more information about the element sulfur. The number 16 in the box for sulfur is the atomic number of sulfur. That number tells us that if we have a sulfur atom, it will contain 16 protons in its nucleus. Now, a molecule is when we have 2 or more atoms, it doesn't matter what type, bonded together covalently. So a sulfur molecule is simply a molecule that contains only sulfur atoms bonded together, like S2 or S8. Sulfur, unlike oxygen, is a solid at room temperature and it generally forms 8-membered rings. Now that we've recapped, let's have a look at our statements. The first statement suggests that sulfur atoms are reactive while sulfur molecules are not. Well, the truth is that the normal form for sulfur is the S8 molecule. You'll see it as a vibrant yellow powder. If you set light to sulfur, it will react with the oxygen in the air, producing a beautiful blue flame and sulfur dioxide gas. Sulfur atoms, if we had them free, would do the same. So the first statement is false and an incorrect answer. The second statement is that sulfur atoms consist of multiple sulfur molecules bonded together. The truth is, it's the other way around. Sulfur molecules contain sulfur atoms. We see things the correct way round in the third statement. A sulfur molecule consists of multiple sulfur atoms bonded together. This statement correctly describes the difference between a sulfur atom and a sulfur molecule, but just in case, let's check the last statement. The first part of this statement is that sulfur atoms can be divided into smaller units. This is of course true. Electrons can be taken off or added to sulfur atoms, forming sulfur ions, and if we try really hard, we can add or remove protons and neutrons from the nucleus. Although in general, we do think about the atom as being fairly fundamental because splitting the atom is quite difficult and releases tremendous amounts of energy. Adding or taking away electrons is much less worrisome. The second part of the statement is that sulfur molecules cannot be divided into smaller units. This is false because we know that sulfur molecules are made of sulfur atoms, so sulfur molecules can be divided into smaller units that are atoms or even smaller units that are protons, neutrons and electrons. To round it all off, let's have a look at the key points. An atom is a positively charged, densely packed nucleus with enough bound electrons to make it neutral overall. An element is just the type of an atom, and it's based on the number of protons in the atom's nucleus. There are currently 118 different confirmed chemical elements, and their information is stored on the periodic table. In the future, we may discover more. And a molecule is two or more atoms covalently bonded together. And lastly, intermolecular forces, the forces between molecules, determine how molecular substances behave, as solids, liquids or gases.